So thank you for having me here. I'm Luke, and I'll be talking my topic on single crystal silicon substrate prepared by Vapour-Liquid interface growth. I refer it to VLIC. So this is the outline of my talk. I'll first start with the introduction, the motivation of this invention, and then basically the setup of this, and a simple model of that, and we're showing that the VLIC can is using a single crystal silicon for making a single crystal substrate, and conclusions. So really our motivations to build up this VLIC to produce a single crystal silicon substrate is because of the current bottleneck in the silicon wafer industry, where we have a limitation in the thickness around 200 micron, and in order to further reduce the thickness, it will cost a lot due to the high kerf loss in the current industry. So this is why we need a new method to produce a very thin single crystal silicon wafers. And it can not only also apply in silicon, but can also apply to any other semiconductor substrates such as gallium nitride and indium phosphide. And due to the cost consideration, that's the main factor that we invent this kind of method to produce substrates. Some challenges in the current industry. First, the current industry producing the crystal silicon is based on the Czochralski or flow zone method, and they are operating at a very high temperature. That's very not cost effective, and due to the high kerf loss, it's having a problem to reduce the thickness to around under 100 micron. There's also some old ancient method that to produce a single crystal silicon called liquid phase epitaxy. It's basically having a problem with detachable problem, so that you cannot actually separate the grown silicon on top of substrate from that. So our goal is trying to find a method to grow a self-supported, and and that means it's very easy to separate from the substrate, and has to be a single crystal silicon sheet so that it can apply in any kind of photovoltaic applications. So back into my master degrees, my research is focused on the VLIC and to develop and implement in single crystal silicon manufacturing. And we also optimize the crystal growth mechanism, such as growth temperature and the growth solution that we use, and also the substrate that we look at that. Finally, we studied the growth mechanism because it's a new invention that we have to take a step into it, and took a look at the interface, and then also we did the electroproperty on the grown silicons. So our approach is simple, and VLIC is basically the modifier from the liquid phase epitaxy. And by taking a look at the left column, it's a conventional Czochralski growth, starting with the crystal growth, slicing, flattening, etching, polishing, and cleaning. So if we take these three steps and combine into one integrated step, so in the first crystal growth, if we lower the temperature of the growth temperature, we could probably decrease the cost in overall. And then in the slicing process, if we have the method to produce the wafer that is being supported itself, and then we can just peel it off, then we can eliminate the dicing or slicing process in a Czochralski or flow zone process. And lastly, flattening. If our method is capable of producing a uniform thickness, then it would be a great improvement to reduce the cost in flattening. So it really comes to us. The solution really comes to us is the bulk film growth by using the Vapour-Liquid phase interface growth. Just a brief description on our equipment setup. We have this 3-zone horizontal furnace tube, and with a purge gas inlet and outlet. The purge gas we use in this case is hydrogen, and the furnace is operating at a very low vacuum. And using these slidables, and this slidable is manufactured by the pyrite graphite, and the function of those slidables is using to hold this kind of compound substrate. The compound substrate is patterned with the 100 micron SIG line inside it. So the substrate will put it inside into this slot, and those big chunk of slots are used for holding the growth solution. The growth solution will be the supersaturated silicon and indium solution, so that when you cool down the temperature, the silicon will diffuse inside to this gap and deposit at this lattice match seed line. So the operating temperature for in the case of silicon would be operating from 975 to 850. It is very low compared with the Chagorowski, which is operating at 1200 degrees Celsius. So this is the process route. It can be divided into three major streams. First is wafer preparation, sort of like a substrate preparation, and the slider bolt assembly, and then finally the growth process. So this is basically one of the sample that we can show. That's the silver strip in here is the ground silicon, and the bluish background is the oxide layer. So aspect ratio is one of the terms that we determine the geometry, or it's basically the width divided by the thickness. So that it's a kind of term to show the geometry of our strip. This is a cross section corresponding to this point, where you have in an aspect ratio around 2.3, and the surface is really smooth in here, and the width for this one is corresponding around to 200 micron, and the thickness is around 100 micron. And this part is the seed line, so it's only a small portion that attached to a substrate, and you can easily peel off once you applied a crystal bond on this portion. You can just take it off from the substrate. The highest aspect ratio we can achieve previously is around 33 in this portion, with the width over 1,000 micron, and the thickness is really around 35 to 50 microns. So it's a very thin sheet that you can actually detachable from the substrate. So this bottom part is substrate. This one is the ground silicon. In this gap, it's just a void. So the growth mechanism is based on three categories. First is diffusion limited. And secondly, it's having a density effect. And lastly, it's having a void enhanced growth mechanism. So first, diffusion is being limited by this kind of structure. So the lower part is the oxide plate, where the vertical growth is being impeded by this oxide plate. So only lateral growth is enhanced. And the density effect is due to the fact that we are using a growth solution combined of indium and silicon. So indium is actually silicon is diffused and melted into indium to reach supersaturation. So indium is a heavier atom compared with silicon. So silicon will tend to float at the bottom of at the top of the solution and deposit at this seed line region. But because of the presence of these bubbles, and these bubbles are the hydrogen bubbles that pre-existing at this oxide layer, keep in mind that the oxide layer is having a poor wettability with this solution. So the oxide layer so the hydrogen bubble will coalesce at the interface of these layers to preventing any deposition of silicon in this region. That's why we have in this gap mechanism in between. There's also some problem using there's some problem with those bubbles that creating a mechanical tear off. In this part, we should have in a 2-1-1 direction, but instead of 2-1-1, we're having this kind of crack off part. So it is because of the presence of those hydrogen bubble, because of the build-up pressure as the silicon sheet is growing into lateral direction, you have this build-up pressure, and the liquid side and the vapor side is having a different stress, so you're causing a crack phenomenon in this direction. And the final step is we can apply a crystal bond to attach on this silicon strip, and then put in two Mylar glass to using as a spacer, and then once it's cooled, you have a very good bonding between the grown silicon and the crystal bond. You can peel off from the top. In summary, this Vapour-Liquid is able to grow a thin sheet single crystal silicon with thickness around 50 to 100, depending on the gap you're using. It also can be, it is operating at a very low temperature compared with the high temperature process in Chicurosical flow zone. So the really advantage is not only it has the feature to peel off, but also operating at a low temperature. And it's not only can use in a silicon, but also can apply in gallium arsenide or indium phosphide. That's our future work to maybe to also use on trying to put on a germanium process. So I would like to thank you guys for coming to this talk, and any question?